Hello, class. Today you're going to solve some just kind of various Pythagorean theorem problems, a bunch of problems having to do with circles, and then just some other problems that require the use of Pythagorean theorem. So let's start by reviewing some of the strategies we learned. So these first three strategies are non-calculator strategies. They're kind of shortcuts that you can use. And then you may need a calculator to use Pythagorean theorem, and then you could simplify the radical or round your answer. All right, so the 45, 45, 90 right triangle is an isosceles right triangle. And we learned that if the legs are of length A, then the hypotenuse is A radical 2. The 30, 60, 90 triangle, so the 30-degree angle is opposite the shorter leg, and then 60 and then 90. If A is the short leg, the medium leg is A radical 3, and then the hypotenuse is 2A. And if you want to work backwards, you remember if you know the hypotenuse, you could divide by 2 to get the short leg. If you know the longer leg, you could divide by radical 3 to get the short leg. And then the Pythagorean triples that you can spot kind of quickly are 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17, along with their multiples. Remember, triples are right triangles whose sides are integers instead of irrational numbers. And then if it doesn't fit into any of those categories, you can use Pythagorean theorem. You can actually always use Pythagorean theorem. So here are some examples of points on a circle. So any point on a circle, if you drop the vertical to the x-axis, assuming the circle center is on the origin, and that's what all of these are going to be, you can form a right triangle. And what's really cool is, well, I think it's cool, but I'm a nerd, the x-coordinate is equal to the base, and the y-coordinate, or the absolute value of the x and the y coordinates, are the legs. So we have x and y, and then the radius is the hypotenuse, and that will always be the case. So we'll be talking about this for a few days. So x, y, and then here's the radius. So in this example, we're looking for the y-coordinate. This coordinate tells you actually the radius. So you go from 0, 0 to 13, 0. So the radius is 13. And this, negative 12. So to plot this point, you go left 12 and then up however long y is. So this is 12. So then you have a right triangle, 12, y, 13. Now, is that one of our specials? Well, it's not 30, 60, 90 because we don't have the angles. It's one of the triples. Whoops. It's one of the triples. So then that is 5, 12, 13. The y-coordinate is 5. And then you just check, it's in quadrant 2. It's above the x-axis, so the y-coordinate is positive. So number 2, we have a point in quadrant 4. Here the radius is 5. The base is 3, so we just need the height. Again, special right triangle, 3, 4, 5. Remember, you could use Pythagorean theorem also. So that side of the triangle is 4. So then what would the y-coordinate be? Negative 4, because it's in quadrant 4. So number 3 and 4, I give you an ordered pair, and I just want to know the radius, or the distance from the origin. Okay, well, draw the triangle. You drop the height. So then you're going 5 to the left from the origin, 2 up. So now find the radius. Is that one of our specials? No, we can't use 30, 60, 90 because we don't know any angle measure. And it's not a triple, so now we're going to use Pythagorean theorem. And then we'll simplify the radical. So 5 squared plus 2 squared equals the radius squared. 5 squared is 25, 2 squared is 4. Square root both sides, square root of 29, and that's a prime number, so that is in simplest form. And just for the heck of it, let's find the approximation. Approximately 5.39. And then number 4, so let's go ahead, draw the triangle. So you go to the right 3 and up 3 to plot the point. And then, oh, that's a special. It is an isosceles right triangle, so it's a 45, 45, 90. So 3A, A, radical 2, so that's 3 radical 2. So here we have number 5. We're given an angle from east, let's say. This actually has a direct correlation to pre-calculus, so you'll see this in a couple of years. But we can use this to figure out the ordered pair. So if we're rotating 135 degrees, then the angle in this right triangle that's formed is 45 degrees. And then you have 90, so it's, 45, 45, 90. And I need to give you a radius here. So I forgot to give you the radius. So let's say the radius is 2. Okay. And a way I could do that is to say this is 2, 0, or 0, negative 2, etc. So if this is 2, so then we have A radical 2, right? So then to work backwards, so 2 is the A radical 2, so we divide by radical 2 to work backwards. And then we rationalize the denominator. So this is technically a correct answer, but we're always going to rationalize the denominator. So times radical 2 over radical 2, and that gives you 2 radical 2 over radical 4, which is 2. So then each part of that triangle, each leg is radical 2. So the ordered pair in quadrant 2 is, let's see, negative radical 2, positive radical 2. And then number 6, let's come up with a radius. Let's just do a radius of 1. So draw the right triangle. Let me change the color for the heck of it here. So we have, so if you have a 210 degree rotation, that means you're going past 180 by 30 degrees. So you're forming a 30, 60, 90. So let's see, A radical 3 is the long leg, and then 2A is the hypotenuse. So the 1 corresponds to the 2A, right? So 1 is 2A. Divide both sides by 2, A is 1/2. And then let's get the long leg. So A is a half, so the long leg is half radical 3. So then the ordered pair will be, so both the x and y coordinates are negative, so negative half radical 3, or radical 3 divided by 2, and then comma negative 1/2. All right, so here's just a new kind of word problem. Calculate the area of a regular hexagon whose side length measures 4 centimeters. Go ahead and sketch a regular hexagon. and each side is 4. And then I'm going to divide this into triangles. What kind of triangles do those end up being? An equilateral triangle. So each angle of a regular hexagon is 120 degrees. And then when you divide them up into congruent triangles, they're all 60-degree angles. So they are equilateral triangles. Okay. So each length is 4. Now, if we want the area, you're going to find the area of one triangle and then multiply by 6. So the area of a triangle is 1/2 base times height. Now, keep in mind, 4 may be the base, but the height is not 4 as well. So the height will be here. Remember, we called that the apothem back in the beginning of the year. So this would be 2. And then, 30, 60, 90 special right triangle, or you could use Pythagorean theorem. And then this would be a radical 3, so 2 radical 3. So area equals 1/2, 4, base of the triangle. Height is 2 radical 3. And then there are 6 triangles, so times 6. So 1/2, so let's multiply all the whole numbers, or multiply the rational numbers, I should say. 1/2 times 4 is 2, times 2 is 4, times 6 is 24. And then times the radical. And we could leave it like that as an exact. Let's just see what that is as a decimal, because that makes a little more sense. Approximately 41.57 centimeters square. So there you go. And then we'll finish with this. This is a classic Pythagorean theorem word problem. Calculate the length of the largest stick that can fit in a box with measurements 5, 12, and 3. So let's sketch a box. So here's the 5, here's the 12, and then here's the 3. Here, let's draw this. Okay, so this one you have to kind of imagine, like, how would you draw that stick to make it the longest? So imagine I'm going to go from this point in the box to this point. So it's not along the floor, it's not along the side of the box, it's going to stand up inside. Okay. Now, I'm going to draw this segment on the bottom of the box. Can you imagine that one? That forms a right triangle along the floor. And then you have the height here is 3. Now, I'm going to connect. Here, I'm going to change the color again. So now I'm going from where I started to the top. So it's going right through the box. And then that's going to form a right triangle standing up inside of the box. Okay, so now you have, let's get this length right here along the floor. So then we have 5 squared plus 12 squared equals c squared. Oh, wait a minute. Do I need to use Pythagorean theorem there? That's a triple, but you can use the Pythagorean theorem and you would get 13. So there's 13. So that's the length along the floor. So that would be the longest stick that would be able to lay on the floor. Now we need to use this right triangle that's standing up inside. Now we will use Pythagorean theorem. 13 squared plus 3 squared equals c squared. Now that one is not a special, so therefore we'll use Pythagorean theorem. So 13 squared is 169, 3 squared is 9. So then you get 178 equals c squared. Okay, and for this, it makes the most sense to leave it in rounded form. So let's take the square root of 178, and that will be approximately 13.34 centimeters. So it can be a little bit longer than just laying on the floor, which kind of makes sense. Okay, so there it is. So you can expect to see a problem like this. Well, you'll have one in your homework assignment, but you will also, you can expect to see one on a test. So if you haven't already, print the rest of the notes just in case you're unable to print. Here are the 3 pages. You're going to turn these in. If you need to, just turn them in on line paper by taking a picture or print them off. So you have a few circle problems, and then you'll have 2 word problems. As always, if you have any questions, please email or come to the extra help session on Google Meet. Otherwise, have a wonderful day.